Okay, apologize for the few-minute delay, but let's get started. So, ladies and gentlemen, welcome to the first talk of this morning session. The speaker is Luca Nenna, who is an associate professor at the Department of Mathematics at Université Paris-Saclay, or Paris-Saclay University, where he has worked since 2024, but I guess before then, right?
Yeah,
Yeah.
2018.
Yeah, 2018. Okay. He is an expert in optimal transport, the calculus of variations, and mean field games, and is going to talk about how an optimal transport problem arises in a counterexample of a conjecture from quantum chemistry for the next hour. Please join me in welcoming Luca Nenna.
Okay, so thank you for the introduction and the invitation. I'm going to talk about this convexity conjecture in quantum chemistry and how optimal transport tool can help us to at least prove a counterexample to this conjecture. And this is a joint work with Simone Di Marino and Matteo Levin. So basically what I'm going to use is just some basic tool of convex analysis. Basically I'm going to convexify some functionals. So I mean, it's pretty easy, almost an undergraduate class. So just take a seat and relax. So everything starts with something that at a certain point we have all been seen in high school maybe, which is the periodic table of elements. So you have here all the atoms that you have in nature. And today we are mostly interested in this number which appears in the right top corner of this table, which is the atomic number. So morally, it's telling you how many protons and electrons are in your atom. And just to have a picture of an atom, you have a nucleus where you have your protons, and then you have just a cloud of electrons around these nuclei. And this number, so for example, 26 is telling you how many protons are in your nuclei, where you have a positive charge, and how many electrons are around it. So again, 26. So basically you have the same number of electrons and the same number of protons. And now you can call, for example, if you have an experimental chemist friend, you can call him and actually ask him to, for example, compute the ground state energy. I mean, at least experimentally of this atom, and probably, I mean, he will or she will manage to do this. And then you can have fun. And so, for example, starting to add some electrons to your atom, so you are charging it negatively. And then you can still compute experimentally this energy, or otherwise you can do something else. So I mean, you can start dropping off electrons from your atom, so you are charging it negatively, and then still computing again the experimental energy of the object that you obtain. And then you go on Wikipedia, as we did with Simone and Matteo, and you choose just three elements. So for example, I choose the carbon and the oxygen, and then you plot the energy, the experimental energy of your atom as a function of the number of electrons. So still you are adding electrons or you are dropping off electrons from your system. So for example, take the carbon. So you have zeta. Zeta actually tells you the positive charge of the nuclei, so how many protons are in the nucleus of your atom. And so, for example, the carbon has 6 protons and 6 electrons, and then you start adding electron and you plot the energy. So you see this is then the experimental energy that you have with your atom with 6 protons and electrons. This is for the oxygen, and this is actually for the zinc. And then what happens if you plot the other experimental energy that you computed? So you see that at a certain point after 7, you do not have, I mean, you still have the energy, but it's going to be constant. The same stuff for the oxygen after, for example, 9 or 10. And then again, if you plot it, you have the energy till you drop all the electrons from your atom. So there are basically some observation when you see this plot. So first of all, they are monotone. So you see that, I mean, the energy is monotone decreasing. And look that when you start dropping of your electrons here, you have some small variation in the energy. So this is basically because, I mean, you are taking the more external electrons, which are the ones that are forming bound with other atoms. So they are actually easier to send them outside the system. And then you need more and more energy to go from, for example, 2 to 1 and 1 to 0. This is because, I mean, you are going to touch the core electrons, so the one next to the nucleus, and so it's actually harder to drop them from the atom. So the first the first remark that you can do is that you can do is basically the fact that this curve, this energy is monotone in the number of electrons. And then, sure, since the title of the talk is some convexity conjecture, of course, all these curves are convex in the number of electrons. And then there is a fourth remark that you see that at a certain point the energy is constant. So I didn't plot it, but I mean you can plot the energy for more and more electrons. But the fact is that it doesn't change, and this is because basically the atom, the nuclei, cannot bind more than a certain number of electrons. Mainly you can start adding more and more electrons, but since the nucleus is not binding them, they actually go to the infinity. And so, I mean, the energy stays constant. And so there is, the constant is a certain point that appears when the number of electrons is larger than the number of protons, plus 1 or plus 2. And so how you can describe all this stuff? So of course what happens is that the way you describe the electronic configuration of an atom, of a molecule, is through the electronic Schrodinger equation. And so you can do this, and then you can try to answer to this remark. So this is actually pretty easy to prove, and we are not focusing on it. But I mean, these two remarks, so the remark number 2 and number 3, actually are what we call the ionization conjecture. Because when you add, when you charge negatively the atom or positively the atom, what you obtain is something which is ionized, so something which is positive charge or negatively charged. And so today I'm actually just focusing on the second remark, and so on the convexity. So it's not pretty, it's a little weird, but so you cannot see us listen and hear an echo. Okay, it's just me. So I'm just going to focus on this convexity remark, and now actually to disprove or to prove that this is theoretically true. I mean, at least using the Schrodinger equation. So let's start to, so every time I will call zeta the number of protons, and capital N the number of electrons. So mathematically what I'm doing is actually try to show the Schrodinger equation. So we have an external potential, meaning this external potential is actually confining potential, the fact that all the electrons must be close to the nuclei of your atom or your molecule. And then what you look in order to describe the electronic configuration is a big function, which is a wave function psi, which is antisymmetric. Why antisymmetric? Because I mean electrons cannot be at the same place. I mean you cannot have the same particle with the same charge, with the same negative charge at the same place. And then you ask that the L2 norm of this wave function must be equal to 1. I do not I won't focus a lot on the functional space that we are going to choose, because it's not the main topic of the talk. I mean, but we can choose the right functional space for everything, and if you want, we can discuss it later. And now, how you compute the energy of your atom? So you define the energy as basically a quadratic form in psi, where this operator is the Schrodinger operator. So you have the Laplacian, which is, I mean, the kinetic energy. Then you have your confining potential V, and then you have the standard Coulomb potential. So this is actually going to model the interaction between the nuclei and the electron, and this actually gives you the electron-electron repulsion of your system. So the main stuff is actually to remember here is that I will going to play with this n and also at the same time with the potential, the confining potential v. And now you describe on the theoretical point of view the energy that I plot before. So the idea is that you can minimize the variational principle, and this variational principle gives you the ground state energy. And I write the ground state energy E as a function of the number of electrons and the potential V. So you just have to minimize over all the antisymmetric wave function psi with norm, with L2 norm equal to 1, these energies. So namely, you are just computing the smallest eigenvalue of your Schrodinger operator. And this is actually the the associated Schrodinger equation. And so all the talk will be based on this object E n of v. And I mean, I will play with the two variables. I will see sometimes as a function of n, and some other time as a function of v. And I'm going to play with these two variables. And of course, depending on the object that you are studying, you have different kind of confining potential. So this is for the molecules, where zeta m is the charge of each nuclei composing your molecule. So you have to imagine that you have some other nuclei over here. And for the atoms, so the case that I show you in the previous slide, you just have zeta over x. So you just minus the Coulomb potential. You see that the confining potential is an attractive guy, because I mean you fix the position of the nuclei, and you want to attract you want your electrons to be as close as possible to the nucleus. And of course, there is a different way to model the nuclei and the electrons, since the nuclei are actually heavier than electrons. So we model them as a classical object. So this is the reason why we fix the position. So you have to imagine that a nuclei is a kind of ball, and then you have a cloud of electrons which are described by the wave function, and these are the quantum particles in your system. So now I can rephrase mathematically the convexity of my ground state E n of v. So the conjecture is, so the remark 2 related to the ionization conjecture is quite simple. So you take some potential V. Imagine that you have the nicest potential ever. So take the Coulomb potential, the confining potential for Coulomb for molecules and atoms. And now you look at this function on the integer n, and you look at the convexity of this function. So this is the way to rephrase the convexity of my experimental energy, right? And so this here is just that for any potential, nice potential V, we want to show that this function is convex in n, with the convention that if you have 0 electrons, then the energy is equal to 0. And the first time this conjecture appeared was in this paper by Perdue, Parra, Levy, and Baldus. They are chemists, so it was 82, and they actually conjectured the fact that this is true for a confining potential for the molecules. And then you have that it was restated in a more mathematical term by Lieb in 83, and then you have again this appears as one of the open problems stated by Simons in his paper in 84. And so now, is this true, for example, for atoms and molecules? So you see that experimentally, this conjecture, we expect that's true. Because I mean, if you plot the experimental energy of your atoms, these curves are convex. And so you expect that this is true, at least for the atoms. And so what happens is that if you have some very special kind of molecule with fractional charges, so it means that we are not exactly in a physical system. So what happens is that the conjecture is actually false. And so what you show is that what you can show is that if you take some very special confining potential, so you can prove that there exists some R1, R6, some positions, some charges zeta 1 to zeta 6, and this small number E4, E2, and E1. And then I will tell you everything about this number. So just remember that we can prove that they exist, but moreover, we can actually have the exact value of all these parameter. Then you define this weird potential. So you see that basically I'm defining a potential for a molecule, but this molecule is a little bit weird because on each nuclei I'm actually posing a fractional charge, because the charge of each nuclei is actually proportional to 1 over the square root of L. And then what happens is that I'm starting to see what happens when L is really large. And when L is really large, I'm actually taking all the nuclei and I'm sending all the nuclei far apart from each other. And what happens is that I'm binding 1 electrons for each nuclei. And so if this happens, and you take the leading order of this of the ground state energy with this particular potential in L, so then what happens is that this the leading order is given by this small E1, E2, E3, E4, but you can go on till E5 and E6. And if you plot it, you see that you obtain this blue curve, which is actually not convex. So you obtain something that at the leading order is not convex. And so what happens is that if you have this very particular molecule with 3 electrons, then the convexity fails, because I mean you prefer having either 2 electrons or 4 electrons, but not 3. So yes, something weird is happening. I mean, what we expect is having this orange curve and not the blue one. So what happens is that this is actually the first counterexample for the Coulomb potential, but I mean, it's of course we are a little bit cheating, because I mean it's not a physical counterexample, since we do not have an integer charge on each nuclei. But what happens is at least that, for example, we can have an integer charge for all the molecule, even if it's not exactly a physical stuff. And all this stuff is going to come from optimal transport tools, and by the fact that we are going to play with the semi-classical limit and see what happens when we rescale the Schrodinger variational principle, and what happens for the classical problems. So let's try to do it. So first of all, so I show you the quantum version of the electronic configuration. So we have the kinetic energy, we have the confining potential, and then the Coulomb potential. And now what happens if we imagine that we have a classical system. And so again, you can define an energy for the classical system. And now I call it the small e of n and v. So you still take n classical particle and the confining potential. And so you can already imagine that the small e appearing here is going to be related to the small e appearing in this theorem. And so now you can, how works the classical n-body problem. So the fact is that now, instead of minimizing over the wave function, you're minimizing over all the position of your particle n particles, and you want to minimize this confining potential again and the Coulomb potential. So you see that going to the classical going to the classical problem, I actually killed the kinetic, the Laplacian term, the kinetic energy. And then you can rephrase the convexity conjecture in the classical stuff. And so what happens is that for some nice v, you look at the convexity of this small e again as a function of n. Okay, so I just rephrase the convexity conjecture, not in the quantum case, but I mean in the classical case. And of course, what happens, what you can do is actually related this quantum and classical problem through the semi-classical limit. So you rescale your functional, you rescale your v, and then with an epsilon, and then take the epsilon going to 0. What you obtain is that your quantum energy is converging to the classical energy. And so what happens is that instead of looking at what happened in the quantum world, we are going to the semi-classical limit, we look at what happens in the classical world, we try to use optimal transport, and then if we manage to prove something about this convexity conjecture in the classical case, we go back to the quantum stuff. So that's the idea. So this problem, this quantum, this quantum problem, this quantum counterexample, we basically built it by using a counterexample in the classical case. And we can do this because, I mean, we have this semi-classical limit linking the two kind of energy. Okay, so just going back to the classical counterexample. So what happens is that we are going to choose a very special V. This V is going to concentrate it on this position R1, R2, R3, and so on. And it's going to have a very specific value, which is given by this. So it's very symmetric, you see. It's a very symmetric configuration. So you have the same value of V on R1, R2, and the same on R4, R3, and on R6 and R5. And the value is exactly this one. I mean, you cannot choose something different, because if you're going to choose to change the second, the third decimals, then everything, the counterexample doesn't work anymore. And here you have the, so I call it ENCL, is just the classical energy. I just take a screenshot of the paper. I do not change the notation, but this is the small e in of the previous slide. And so you see that what happens is that you have this value from 1 electron, 2, 3, 4, 5, 6. You cannot have more than 6 electrons, because I mean you are forcing your system just to fill 6 very precise position in the space. And then if you plot this energy, what you obtain is that it's not convex, because if it was convex, then you should have something like the orange curve, and not the blue one. And of course, you see that with respect to the quantum energy, here at a certain point after 4 electrons, you go up. This is actually basically because you are in a confined system. So at a certain point, you cannot bind more, and the electron cannot escape to infinity. And so at a certain point, you have that the energy goes up again, but that's not a problem. And then how you build this potential VL? Well, this charge is basically built by using the value of the potential Vm of the classical stuff. And so basically what's happening is that I'm choosing this position. I put a nucleus on over these R1, R2, R3, and so on, and giving them enough charge to bind just one electron. So in the quantum case, I'm forcing the electron to stay exactly at this position in order to retrieve what we have at the classical level. So now why this classical counterexample works, and this is the moment where we are going to use convex analysis. So first of all, I mean, you can rewrite this classical quantum body in a different way, because I mean, you see that previously this E, you can write it as an infimum of all the position, but actually you can write it as a minimization over some probability measure which are symmetric, and that's because the extremal point of the probability measure are the Dirac. And so, of course, what's happening is that if you minimize, is going to be on this position x1, x2, x3, x4, xn. So basically, you have exactly the same value here and here. So already I'm kind of relaxing. So now I lift my problem on the probability measure, and I'm a guy from optimal transport. I love working with probability measure. I'm more familiar with them than with just x1, x2. And of course, here you're minimizing this functional, which is linear in P, and you have this function given again by the confining potential and then the Coulomb potential. And then, well, you are looking at the convexity of this function on the set of integrals. So what you can do is actually convexify it. And the way you convexify this function is actually take it on the real positive number. So I define what is called the grand canonical energy. And now the grand canonical energy is just a convex combination of all the energy for all the possible integer n. So I'm just doing an infinite sum of the ground state with small n electron. I'm weighted with Pn. So Pn is the probability of having n electrons in your system. And then, of course, what happens is that the sum of over Pn must be equal to 1, because this is a convex combination. And then the other constraint is that if you weighted Pn with n, just because here we are using a symmetric probability measure, then this must be equal to lambda. So in some sense, what I'm allowing with this convexification is that now in my system I can have a fractional number of particles. So in other way, the grand canonical ensemble in statistical mechanics means that I have my system. So my system is communicating with the reservoir, and now I can exchange particles with the reservoir, but I do not know exactly how many particles are in my system. And so this is the reason why instead of having an integer number here, we have now just a positive real number. So, but from the point of view of convex analysis, what I'm doing is just a convexification of my function. And so, of course, if I have small e is not convex, well, it doesn't mean if I evaluated his convexification, his convex hull in exactly lambda equal to n, then they must not coincide. So in other words, I can rephrase my convexity conjecture by using the convexification. And so the conjecture is true if and only if these two energies coincide for any integer. Of course, if En is not convex, it means that he lies above the graph of the grand canonical stuff, because I mean this is the convex hull is actually the largest convex function below my function e small e n of v. So you see that if I want to disprove my conjecture, I just have to show a case where these two energies are not equal, because I'm just using the convexification. But still, it's a little bit more difficult. It's a little bit difficult because I have to find a very specific potential V. I do not know exactly how to do it, and so I use again convex analysis. And now convex analysis tell me this. So you fix your force variable n, and now I'm starting play with the second variable, so with the potential V. And what happens is that these two quantities, so the classical energy and the grand canonical energy, are concave in V. And so since they are concave, I like doing convex analysis. And so what's happened is that I took the Legendre transform. I took the Legendre transform, and so instead of using V as variable, I go to his dual, and now the dual is just a density. So just to give you again the picture, so I have the quantum case, the quantum energy. So I'm going to the classical one. So I have now E and V, and now I'm looking either in the V variable or with its dual by using the Legendre transform, and the dual is just the electron density rho. And so now if I dualize this problem, so if I took the Legendre transform, so basically is this stuff, so I maximize over V minus the dual product between V and rho. So what I obtain is this object C of rho. And C of rho is something that at least I know very well, because I mean this is actually an optimal transport problem. So what happens is now that I'm minimizing over all the symmetric probability measure living on R3n, and I'm actually giving a constraint, and this constraint is that each marginal of P, so the projection of P over just R3, must be equal to rho. So the dual variable associated to the confining potential V. And so now instead of working with the energy NV, I'm going to work with the optimal transport term, and remind just that the total mass of each rho must be equal to n. So this is the way where you keep track of the number of electrons, the total mass of rho. So it's not exactly a probability measure; it's a probability measure times n. That's not a big problem. And then you can define again the same stuff, but on the grand canonical level. And so, of course, it's again a kind of convexification. So you just have a convex combination of all the optimal transport term with small rho n. So meaning that rho small n has mass equal to n. That's exactly the same stuff that I did before with just the energy. And now I can rephrase the conjecture, because I mean I can go from my E to his Legendre transform, and then if I take the Legendre transform of C, I find again E, due to the fact that I'm working with convex stuff in V. And so how can we rephrase the conjecture in this case? So the conjecture now is true if and only if the value of these two problems coincides for any rho such that the total mass of rho is equal to n. So you see that now I do not have to find the V, I just have to find the rho such that the two energies do not coincide, and then I take the corresponding V by using duality. And that's the way I can disprove the conjecture. So, but now, how can we do this? So the idea is that we have to find a way to prove that this grand canonical optimal transport problem do not coincide with the canonical one. And so the way we do it is just, we have to prove that when we take the minimizer of this problem, then the minimizer is such that I prefer doing a combination of optimal transport. So it means that the minimizer is, I want I want many Pn and not just one Pn equal to 1, because you see that if it exists a Pn equal to 1, it means that my two problems coincide, because my grand canonical is finally canonical. And so the idea is actually looking to the support of this problem, but just before going to this, so what we can do to the quantum level, because of course I'm using duality on the classical one, but if you want, you can use duality also on the quantum one, on the quantum problem. And what happens is that you can still have a dual problem, and this dual problem now is very known in theoretical physics, it's in quantum mechanics, because I mean it's what we call the Lieb functional, and this functional actually keep track of the kinetic energy and the electron repulsion of an atom of a molecule. And moreover, it's a universal function. It means that it does not depend on the nature of your atom of a molecule. And again, you can restate you can find the grand canonical Lieb functional, and you can restate the conjecture in terms of the Legendre transform of the quantum energy. The reason why we do not look at this is actually because it's too difficult to work with this functional. And so if we go back to our classical case, so the idea is that now we want to study the support of the optimal collection of Pn. And so what's the support is just now the n such that we activate the Pn. Okay, and then we want all the other Pn equal to 0, meaning that we have probability 0 finding n particle in our system. And what we can prove is actually that if any optimizer of the grand canonical has this kind of support, so the support is exactly one capital N in the case when n is equal to 0, 1, or 2. So now I take in just a rho which has an integer mass, so this is the way I compare the two. And then the support is actually proportional to the square root of n if n is actually larger than 3. So in some sense, he's telling that in this case, you have equivalence between the two energy. In this case, it means that the grand canonical energy is going to be smaller equal than the canonical one. But we can do something more, because I mean, we can find a rho, a very specific rho, such that the support is always with total number of electrons equal to 3, and the support is just 2 and 4. It means that you have just a combination of 2 electrons. You can have just either 2 electrons in your system or 4 electrons. And you have probability 1/2 of having 2 or 4 electrons. And what happens is that the grand canonical energy is going to be strictly smaller than the canonical one. So in other terms, what this theorem is telling you is that the convexity conjecture doesn't hold for this very specific density. And of course, you can work with this density and create a bunch of other densities such that the support is always concentrated on this stuff, so it becomes larger and larger, and you always have a strict inequality. So now the question, how this density look like? And so what happens is that this density is just the sum of Dirac concentrated on these R1, R2, R3, R4, R5, R6. And we are giving just one, it's what we call the alpha filling, meaning that we have 1/2 probability of having one electron here, 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 or on the other position. So we are fixing the measure rho to be to some very precise position. And then what happens is that you can compute the grand canonical energy and the canonical one, and you obtain that this actually stricter. But what happens is that a very, very particular configuration. So you see that in some sense is very degenerate because I'm adding a lot of symmetries when I build it. And for example, if I just move a little bit R3, then the two energy actually becomes equal. So I mean, we obtain this strict inequality in this very specific configuration. And so this is exactly the R1, R2, R3, and so on that we use in the quantum counterexample. So we have the classical counterexample, and by using what we know about it, we build the quantum counterexample that I showed at the fourth slide of this talk. And then you can build some other, say, bunch of other counterexample, but just by using, by repeating this pattern as here. So now this is the density where it's concentrated, and you can again use it and concentrate the nuclei of this fake molecule on each of this position. So then what happens? You want to find the V, the corresponding V to this rho. So what you can do is just using duality and using the potential coming from the grand canonical optimal transport. But what happens is that if you use this potential, you obtain that the free energy are actually equal. But I mean, then you can use this as initial point and try to minimize what you want to show that it's not convex. Actually, you find the value V1, V2, V3, V4, V5, V6 that I showed you before, and this is exactly this point. And you magically find this counterexample, the right potential to use in the quantum counterexample. So just to be honest, I mean, it was. I mean, we were quite lucky to find this configuration because at a certain point we wanted to find a configuration where these two problems, where we have a strict inequality, so we start a big simulation with billions of points in the cube, in the three-dimensional cube 0, 1, and we find this configuration. I mean, it's a little bit cheating because we are in 3D, but actually I'm putting all my electrons on a plane. So that's the way we found it. So some more remarks. So when the convexity conjecture holds in the classical case, so I mean it's true when the electrons are on the real line. So this is actually because I mean the optimal transport problems becomes a one-dimensional problem. In one-dimensional, when you want to find a minimizer to your optimal transport problem, it's always easier because it depends on the structure of R. And then it also, for example, if you take again the same example as before, but instead of having 6 Dirac, you just have a measure concentrated on 4 Dirac. And this was exactly the example by Lieb, and the fact that Lieb didn't manage to prove it for some potential. And so of course you can ask yourself, okay, maybe we can use exactly the same tools. So because basically what we use in the classical case to find the counterexample is convex analysis and then study the minimizer of our functional. So you can do the same, you can try to do the same stuff in the quantum case. So you look at the Legendre transform, you have your Lieb functional, you convexify it, you have the grand canonical, and then you study the minimizer of the grand canonical Lieb function. The problem is that it's way more difficult studying this minimizer, and we do not have the same result on the support. This is basically because I mean we do not manage to take some optimal transport tools and to rephrase them in quantum terms. And so we cannot have exactly the same proof as for the classical problem. So it's way not obvious. And so I think that I'm almost done. And just to conclude, so this is actually what we can prove is that in general this convection is wrong for Coulomb potential. So, but be aware the fact that the tower counterexample works in a very specific case. So when we have a fractional charge. So for example, we do not know yet how to prove it when we put some integer charge on the nuclei of our molecule. Another way we cannot prove it, at least in the case where in the physical case where we have integer charges. But the fact is that in general, this also if we have fractional charges, this is actually interesting for chemists because sometimes for their computation they use fractional molecule with fractional charges in order to approximate the energy. So for them is already interesting the fact that for fractional charges the conjecture does not hold. But I mean, still, of course, open if you consider atom and molecules. I mean, real molecules, and that's basically. But the problem is that we have no idea why it works. So experimentally, we know that for atoms and also numerically for atoms must work. The problem is that when you go when you start studying molecules and we do, for example, numerics for molecules, we have this conjecture, I mean, does not work, and we do not know if this is actually related to the numerical method that we use, to the specificity of the computational method for computing the energy for molecules, or if instead, I mean, it's really not true for molecules. So that's exactly what I said, but still we do not have a mathematical intuition of why it's working. Another stuff is that I show you that, for example, if you have electrons on the real line, the conjecture is true in the classical case, but for example, we are not able to prove it the same in the quantum level. So forcing the electron to stay on the real line and to have the quantum counterpart of this example. Actually, so I mean, basically, I use just tools from convex analysis. Okay, a little bit of optimal transport, but mainly convex analysis. So just convexification and Legendre transform. And so just, I mean, a remark, because I mean this 2025 is actually the 100 years birthday of the Schrödinger equation, and actually still quite nice the fact that you have a lot of problems, again, still open problems related to this equation. Or at least, of course, I show you a very particular Schrödinger equation because it's the static one where there is no time, and so on and so on. And so some referencing the thing that I'm done with this.
Okay, do we have any questions for Luca Nenna?
Maybe I have a naive question for one of your very first slides.
Okay.
So where you showed this convex plot, and somehow it looks like when the number of electrons goes up, the energy goes down. But then if it becomes very big, shouldn't it go up again?
So I guess, okay.
So if the number of atoms is bigger than, or much bigger than the charge of the kernel, shouldn't it go up again?
Oh no, because I mean this is not a confining potential. So I mean what happens is that you cannot
just
bind and they go to infinity. So of course this is the case of the quantum. This is the quantum case, but if you are in the confined, the classical one, the confined that I showed, this is the reason why at a certain point when I plot it, it was going up because it was confining, and so they cannot escape to infinity.
Thank you.
Any more questions? I have I think it sounds like you could do it. You have a perturbation result, though, right? Because you have a strict inequality.
Yeah.
So somehow there's like a very narrow region around this counterexample.
Yeah. We know. I mean, we know if where is down the plot. So it's not exactly true the fact that if I move R3, it's immediately wrong, the stuff. I have a small region around here or around each point such that the strict inequality still holds. But for example, we do not know how to quantify this region.
I see. So you don't know, but you know from test examples if you change it by, say, 2 decimal points.
Yeah, that's, I mean, yeah, a little bit exaggerated the fact that if we change it to 2 decimal points, then everything wrong. You have to go a little bit farther to have the equality.
Okay, and that's perturbation in row.
Hmm?
The argument is perturbation in row, right?
Yeah.
Okay. Any more questions? If not, let's thank the speaker. Thank you again.